Okay, welcome uh, to the Electrical Machine 1 lectures. In the previous lecture, we have discussed some basic of DC machines, DC generator, DC motor, and working operation. So, because it consists of many part of the DC machine or DC motor or DC generator, so it is necessary to understand with the help of some proper diagram. So today we will discuss with some proper diagram. So this is the main classification of DC generator, DC machine. So first is the DC machine. So machine may be a generator, it may be a motor. So for our motor, when the input to the motor is mechanical, input to the motor or machine is a mechanical input, and it converts mechanical input into the electrical output, then it is called as a DC generator, or simply it is a generator for the machine. And when we discuss about the DC machines only, so we will call as a DC generator. Whereas if the input is electrical in the form of electrical energy, which is equal to V is the power voltage into current, that is much is the watt multiplied by time is the energy. So input is the electrical energy and the machine convert into the mechanical energy, then it is called as a motor. So this is the things. This is the basic main classification of DC machine. One act as a DC generator. When mechanical energy converted into the electrical energy, it is called as a DC generator. And when electrical energy is converted into the mechanical energy with the help of machine, in between this is machine, and then it is called as a DC motor. So this is one. Now the filming right hand and left hand rule already you have learned in the, it may be in 11th or 12th standard. But again, we will discuss because we are going to apply this filming left hand rule and right hand rule in the, say, in our discussion, isn't it? So here, see, this is the right hand rule. The thumb shows the motion of the conductor or force acting over the conductor. The first finger shows the direction of magnetic flux, and the second finger shows the direction of current. So right hand rule is used for the generator. It is used for generator. This is the permanent magnet. This is north pole and this is south pole. The magnetic flux always initiate from north and terminate toward the south. So this is the direction of magnetic flux. So your first finger shows the direction of magnetic flux. We are moving the conductor by some means, or it might by hand, in upward direction. So this is the direction of force. So the EMF induced in the conductor or the direction of current in this way. So this is the direction of current. So as the current is coming toward us, so it is represented by dot, isn't it? Because if you represent the current with the help of arrow, and this is the, if the arrow coming toward us, so you will find this is the direction. And if the arrow is going away, then we will find from the back side. So this is cross. So this is dot and this is cross convention of the current or EMF induced. So filming right hand rule says that if we stretch our finger mutually 90° to each other in such a way that first finger shows the direction of magnetic flux, the thumb shows the direction of motion of the conductor, which is externally applied to the conductor. Then the second finger shows the direction of current or direction of EMF induced. Whereas filming left hand rule, it is used for the motor. It is used for the, to find out the direction of rotation. Now here the given quantity is current and magnetic flux, isn't it? Here the given quantity is force and magnetic flux, and this is unknown quantity. We are going to find out the direction of EMF induced, isn't it? And this is here, the force is the unknown quantity. Now, if you stretch the finger in such a way that your first finger shows the direction of magnetic flux as usual, The second finger shows the direction of current in the conductor. So whenever the current carrying conductor plays in magnetic field, it experiences a mechanical force whose direction is determined by Fleming left hand rule. So this is the direction of current in the conductor, which is known to us. This is the direction of magnetic flux. Then the conductor experience the force to the upward side. So just I will repeat for the generator. Whenever the conductor cuts the magnetic flux, it experiences or it induces EMF. Whereas the current carrying conductor plays in a magnetic field, it experiences mechanical force whose direction is given by the Fleming left hand rule. So very simple right hand rule for the generator to determine the direction of current or to determine the direction of EMF, whereas Fleming left hand rule is used in the motor to determine the direction of motion of the conductor or force acting over the conductor. Now, just Faraday's law of electromagnetic induction. This is the coil which is connected with the galvanometer. If you just place the some permanent magnet stationary, it will give the deflection. Momentarily, it will give the deflection, and again it come to the zero position. It come to the zero position. Say this is the zero position because we are not moving. But as soon as you move the conductor, if you move the either this coil, if you are moving, or if you are moving this permanent magnet inside and outside, just so because of the change in magnetic flux, it induces EMF, and you will find the galvanometer deflection in one direction, in one side, and in the opposite direction. If you withdraw it, so you will find in the opposite direction, isn't it? Depend upon direction is depend upon the EMF induced. So it means that the EMF induced in the conductor is given by rate of change of flux linkages. So EMF induced in the coil is which is given by Faraday's law of electromagnetic induction. So E is equal to minus d phi by dt. It is the rate of change of flux linkages because of the movement of the permanent magnet. And there are n number of turns. Turns already we have discussed. Two conductor will make turns. So this is one conductor, say this is second conductor, and like this is one coil, this is second coil, this is third coil, and now n number of conductors are there. So here n, it indicate that n is the number of conductor, and d phi by dt is nothing but the rate of change of flux linkages. And minus sign is as per the Lenz's law. It says that the EMF induced in the conductor in such a way that it opposes the creation of magnetic flux, or it opposes the change of magnetic flux by which it is going to produce. Okay. So now for the generator, what we will do, we will place north pole and this is south pole. The magnetic flux created from the north pole and terminate toward the south pole. It is equally distributed over the rectangular part of the permanent magnet, and one conductor is placed under the influence of magnetic flux, isn't it? Now, initially, the EMF induced in the conductor is zero, but as soon as if you move the conductor either from the upside or either from the downside or by up and down like that, you will find the EMF induced E. This is the EMF induced in the conductor, which is given by Fleming right hand rule. So it is Fleming right hand rule. The direction of EMF induced in the conductor can be found. So this is the basic of the dynamically EMF induced. So it is the Faraday's law of electromagnetic induction. It is dynamically because either the conductor is dynamic, either the conductor is moving or the magnet is moving. So in this case, the magnet is permanent. This is the magnet is stationary. Here the coil is stationary. So either you place the coil stationary and give the moment to the permanent magnet, or if you place the permanent magnet stationary, you have to rotate the conductor or you have moved the conductor under the influence of magnetic field, then it experiences or it induces the EMF. So this is the basic fundamental of generator. Okay. So now operation of the generator is very simple. Here we have placed a coil which is made up of two conductors. This is AB is a one conductor and CD is the second conductor. It is connected from the back side. And now as it is rotate in any direction, it may be a one direction and this one. So under such condition, the conductor cuts the magnetic flux and it induces EMF whose direction is given by Fleming right hand rule. And now when we connect with the help of some brushes, this is brushes which is placed over the rotating part, because it is rotating and we want to collect the current for the stationary circuit. It is necessary to have some slip rings or commutator which we are going to learn, and there is a over the brushes. If you have seen many times, if you just remove the your home mixer, if the motor is not running, you will find some carbon brushes are there, isn't it? So now the current is going to flow in the external circuit, that is a load circuit over this one. So now if you move the conductor, it rotate one direction, the EMF induced is alternating, which already we have discussed. In the in the 0 degree, EMF is 0. At 90 degree, it become maximum, and again goes to the maximum negative, equal maximum negative. So it is V maximum, and it is omega t angular moment, or it may be a 90 degree, 180 degree. This is 270 degree, isn't it? And this is 360 degree. So it will give the positive half cycle and negative half cycle. But for the DC generator, we want the current in the external circuit is the unidirectional, means we want only the positive half cycle in one direction. So for that purpose, we have to connect the conductors, that is a coil, with the commutator. This is the commutator. What is the commutator? Half of the coil is connected to the one part of the conducting media, and in between this is the non-conducting. This is insulator. So when the conductor moves, so in the one direction, the current is going to flow. Say let the current is going to flow in this direction. After half an cycle or after half rotation, this E comes over here and F goes to in this side, say in this diagram. So what happened? The current in the external circuit will remain same. Say in the positive half cycle, the current in the circuit is from Y to X, and from negative half cycle or half rotation of the conductor, the current again remain in the same direction. So it is going to happen with the help of commutator segment. So in this case, what is the difference between AC generator and DC generator? In case of AC generator, instead of commutator ring, there is a solid ring is there, that is called as a slip ring. So this is the rotor circuit which is going to rotate inside the magnetic flux, and all the conductors are connected to the slip rings, and with the help of brushes we can collect the current in the external stationary circuit, isn't it? So it is a solid ring. Whereas for the DC generator, it is called as a slip rings, isn't it? Whereas in case of the DC generator, it is a commutator. See here, these are the number of conductors over the periphery of rotor, isn't it? This is the ball bearing on the both side, and all the conductors are connected to the commutator segment. So it is quite clear from this one, there is some segments are there. So one is the conducting media, now there is a non-conducting, then again conducting. So when we place the brushes, it will conduct the current in only positive half cycle. So this is the insulator in between the segment, and this is the coil which is connected to the commutator, that it is made up of copper, and over which we will place the brushes, and with the help of brushes we can collect the current, isn't it? So this is the things. Now see the principle of operation as a this is the operation as a DC generator. So here the conductor or coil is moving under the influence of magnetic flux, whereas a brushes is placed over the commutator segment. So this is half segment, this is second half segment, and when it is going to rotate, the current in the external circuit is only positive half cycle. So it is only positive half cycle. So therefore it is called as a DC generator. So it is clear from the diagram. This is the armature. This is the number of conductors placed to obtain the required amount of voltage. Let this conductor is producing 1 volt. This conductor is producing 1 volt. So the total voltage across the load or this one, it will is the 2 volt. But if you want 200 volts, so what we have to do? We have to place 200 conductors, which is arranged over the periphery in such a way that it will make some rotating part. And to support that rotating part, it is the shaft of the motor, shaft of the rotor. There's a ball bearing both sides, and over which we will place the armature winding, that is called as a armature. The winding where EMF induced is called as a armature. So it is a armature winding. It is connected to the commutator segment. Now in this diagram, it is quite clear. See, this is the commutator's copper bar. It is a conducting, and in between, this is the non-conducting one. So by this way, we can obtain the unidirectional current in the external circuit with the help of commutator segments. Now, field and armature winding. Field, in case of the permanent magnet, the magnetism or the flux created by the magnet is gone decreasing with the aging effect. And second is that the flux produced by the permanent magnet is constant. It is constant, or it is not possible to control the magnetic flux for the different application in the DC machine, isn't it? It may be a motor, it may be a generator. To control the magnetic flux as per the requirement, it is not possible to use only the permanent magnet. Therefore, we are using electromagnet. So what is electromagnet? The magnetic material is there, silicon iron, and over which we will do some winding. So we make some winding, and it is energized with the DC source, or it is the resistance over this one, and it is a controllable. So if you control the current in the coil, definitely the flux produced by electromagnet is going to control. So instead of using the permanent magnet, some magnetic material is used. It is a laminated magnetic material, and over which winding is carried out. So this is the coil, or this is the field winding, which is responsible to produce the magnetic flux or field and over the periphery of rotor, isn't it? And now this is the armature winding. Armature winding is the winding where EMF induced. So this armature winding, again, this is the armature structure. It is made up of silicon iron. It is made up of silicon iron, one thing, and it is a laminated. It is a laminated. What is the meaning of laminated? It is made up of number of strips, and they are joined together in such a way that in between the strip, say this is the gap in between the strip, there is a insulation, or there is some varnish are going to place, and because of this one, it will become a laminated. It will reduce the eddy current and hysteresis loss. Okay. Now this armature conductor is connected to the commutator segment. Now armature winding. There are two types of armature winding. One is the lap winding and second is the wave winding. Lap winding is used for medium voltage and large current. Lap, see, this is, say, for example, this is one battery. Already you have learned something batteries. Okay, say this is 2 volt, 1 ampere, isn't it? Now second battery, 2 volt, 1 ampere. Now if we want medium voltage, this is 2 volt, but the current should be higher one. So what we will do, we will connect into the parallel. Now this parallel is connected with some external load. So what happened? The current will be a 2 ampere, whereas the voltage across load is 2 volt only because it is connected in parallel. So similarly, in the lap winding, the number of conductors are connected in parallel, or number of coils are connected in parallel to obtain the large amount of current and medium voltage, isn't it? So this is the Diagram of lap winding. Number of coils are connected in parallel to the commutator segment. This is the commutator segment. This is commutator segment. This commutator segment is connected to collect the current with the help of brushes. So we will place the brush over here. This is to say, this is brush, and we are collecting the current from the brushes, isn't it? Because it is a rotating part and brushes are just placed. It is a stationary part, so it is easy to collect the current from that stationary part. Whereas if you want the current voltage should be large, say this is one 2-volt battery. This is one more 2-volt battery. It is connected in series, 2 volt, and now it is connected to the load resistance. So now what has happened? The voltage is equal to 4 volt. And whereas the current in 1 ampere, this is also 1 ampere. We are using same battery. The current in the external load is only 1 ampere. So here the voltage is going to increase. So in case of wave connected, the number of conductors are connected in series. So here we are able to produce the large voltage and medium current. So this is the application of lap winding and wave winding in case of DC machines or DC generator. Now armature core. Armature core, say this is the one wafer or one strip of the armature structure. Now there are number of such type of plates we are using to make the structure. So this is the structure which we have used. This is used for the cooling purposes. It will provide some cooling. This is for the shaft, and these are the grooves over which we will place the number of conductors. This is called as an armature conductor. Number of armature conductor placed inside the slots or grooves made over the periphery of armature. And now these armature conductors, they are either it is connected in lap winding or either it is connected in wave winding, and it is connected to the commutator segment. So this is the commutator segments are there, and in such a way we are using the armature core. But the armature core, since we found that the actual EMF induced is always alternating, isn't it? And because of the alternating, it induces current. See, this metallic part is there. This is the made up of silicon iron. It is a conducting part. So current, this metallic part also induces some EMF, but it does not find any closed path or any external circuit. Therefore, the current flows in the form of eddies over the surface of this metallic part or iron part, and these type of current or EMF induced and that it drives the current, it is called as a AD current. It is called as a AD current. And this AD current rise AD current power loss. So it will give the power loss inside the machine, isn't it? To reduce that AD current power loss, the structure is made up of laminated. Laminated, what is the meaning of laminated? This is one strip. Now the second strip is there. In between there is a varnish, means the complete structure is dipped into the varnish and then it is back into the oven. So every plate is laminated, every plate is insulated to the next plate. And that's why the resistance also get increases. It is depend upon the thickness of the lamination, and hence it is possible to reduce the eddy current loss. Whereas this is not, it is made up of magnetic material. Soft magnetic material is there. It may be a say silicon iron, or say it is called as a ferromagnetic material. Okay. Now core, this is the pole structure and field winding. So similarly, instead of using the permanent magnet, we are using the electromagnet. So to make the electromagnet, we want magnetic material. So this is the magnetic material. Again, it is laminated and over which the winding is carried out. So this is the pole core and this is the pole shoes. This pole shoes especially made to spread the magnetic flux equally over the periphery of rotor or periphery of armature. So now here the winding is carried out over this one. So it is called as a laminated core. It is called as a laminated shoes, and this is called as a, it is called as a field wind, whose responsibility is to produce the magnetic flux over the periphery of armature, isn't it? Magnetic flux. Now, so this is somewhat pre-final say structure of DC generator. So we will start. This is the yoke, which is support the stationary and stationary and rotating part of the machine, and it is serve two purpose. It also carries the magnetic flux produced by magnetic poles. So this is the path of magnetic flux it is going to complete. Let this is the north pole, this is south pole, this is north pole, this is south pole. So flux is going to create from north terminate to south. So it serves two purpose. One is to carry the magnetic flux, and the second is to give the mechanical protection and support for the all uh, say rotor as well as stator, isn't it? No, this is pole core. This is pole shoes, already we have discussed. And this is the field winding, which is connected in series to produce the magnetic flux. So there are four conductors are there. This two conductor is used to excite the magnetic flux or to produce the magnetic flux with the help of electromagnet. That is called as a field winding. So this is field winding. Whereas this 2-1 is used for the armature. Whatever the EMF induced in the armature, it is get connected over the, these are the armature conductors. This is the armature conductors are there. These are the armature conductor. It is connected to the commutator segment, and over the commutator segment, 4 brushes are placed. 4 number of poles are there. 4 number of brushes are there. When the rotor rotates, the brushes are stationary. Only the commutator segment is going to rotate. So in positive half cycle, it will conduct the current. In the negative half cycle, because of the non-conducting media between the segment, so it does not conduct. So we will find with the help of commutator only unidirectional current into the external circuit. And this is the terminal box. So this is the some part of the DC generator and DC machine, DC motor. So this is some three-dimensional view. This is the pole core, field winding. The pole core and field winding function is to produce the magnetic flux over the periphery. There is a pole shoes which will use, which is going to produce the spread the magnetic flux equally over the periphery of armature. This is the shaft, bearings, and this is the commutator segment. So this is the commutator segments are there, and armature winding is connected to the commutator segment, and this is the armature. Okay, so armature winding, here is the armature winding, field winding, this is field winding, and this is the some yoke which is used to carry the magnetic flux as well as to give the protection to the rotating and stationary part of the machine. So now this is the complete picture of the DC machine. Now this is the rotor. Rotor carries armature winding. Armature winding is connected to the commutator segment. This is the armature conductors are there. It is coming from the slot over the periphery of rotor, and it is connected with the commutator segment. So this is the commutator. Complete commutator is there. This is the bearings, end rings, the fans are there. Because continuous operation of machine, it will give the heat, it will produces the heat, and to give the proper cooling, we can provide the fan to the one end of the machines. Yes, so this is the shaft, again ball bearing, and here there are some, say this is the, say, yes, this is the stator. Stator is the stationary part of the machine which carries the armature, which carries the field winding and field pole, field shoes, and all these things. So this is the complete, say, diagram of and cross-sectional view of DC machine. Now this is the brush holder which carries the brushes and it is placed. See, this is the carbon brushes. This is the carbon brushes which is placed over the commutator. Means it is continuously touching, just similar to the pantograph of train. You have might observe that. Suppose this is the train locomotive is there. It is going to run over the track, whereas it's going to collect the current from the overhead conductor. So you will find such type of pantograph over the roof of electric locomotive. So it is stationary and it is the moving part. So it is just rubbing or touching and collecting the current from the overhead conductor, and then there is some machineries, transformers, cyclo converters, and all these things. Motors are there. Similarly, the brushes are there, which is analogy to the pantograph of the train or locomotive. So now this is the inside view of DC machines. Again, this is the armature. This is armature structure. Armature, it having slots over the periphery of rotor where the conductors are embedded or the windings are carried out, and these winding terminals are connected to the commutator segment, and it is the end rings and some this one. Now this is the pole shoes, which is curve in shape, which we have already seen. This is such type of structure is that. Okay, so you will find this is the structure, pole shoes is there, and this is the winding, field winding. This is field winding is there, and it is brush holder. So this is brushes. This is field coil. It is pole shoes, isn't it? And this is field winding bobbin. Bobbin is there. So some winding is carried out. Now this is the complete structure. So this is the field winding. Okay, this is field winding, field poles, and inside it is free to rotate. So this is the complete structure of DC machine. Now this is the enclosures. Enclosures, there are different type of enclosures are there. So some vans are provided for the cooling purpose. See, it is a cooling purpose. But if these vans are very much open, we cannot use such type of generator and motor in the dusty area like cement factories or where dust and dirt is there, or we cannot place into the atmosphere or outdoor purposes. So we have to use the motor or the machine which is totally enclosed. So it is a totally enclosed. Totally enclosed. Here there is no such one, but here the fans are provided for the cooling purposes, and depend upon the application, the enclosure of DC machines or any type of machines we are going to use. Say for example, if the machine is going to use in the outdoor purposes, so it should be a weatherproof, waterproof machines, waterproof enclosures are there. If it is used in dirt and dust, so it should be a free from dirt and dust. If there is a large heat is going to produce, the motor surface will be a like this. Say some vents are provided for the extra cooling. You have might seen such type of surface. So it is used for the cooling purposes. If the motor is used or machine is used in petrochemical or chemical industries where methane, ethane gases are there, so it is not in such a way that there should be a terminal should not be open like this one. This is the open terminals are there. It may catch the fire. So it is a flame proof also there. It is a flame proof. It means that if there is some sparking, it will remain inside the enclosure. So these are the some things which is related to the construction and basic working operation of DC generator. Now, when we are going to learn with the help of books, like in the BL Theraj or somewhere books, you will find such type of diagram. So it will give the same way. So without any slip rings or without any commutator segment, the EMF induced in the DC generator is always AC. So basically the EMF induced, dynamically EMF induced is always AC, and with the help of commutator segment, it is possible to convert the bidirectional current into the unidirectional current in the external circuit. So here it is a commutator segments for the two we are using. This is the brushes and this is the slip rings, and here the current in the both direction. But if you use the commutator segment, this is the one conducting media, this is second conducting media, in between there is a non-conducting. So what happened, once the conductor rotates, so the segment get changes, position get changed. Say A and B is here. Now here the B is here and A is will be here. So the current will remain in one direction. So current is in the unidirectional, which is shown by this one. So this is the way in the book you will find such type of diagram. So do not confuse. So this is the commutator segment. This is the brushes. Especially, I have taken the diagram from the book so that once you are going to read from the book, it becomes easier to understand the construction main part, the function of each part very easily. So again, the same thing is there. We have seen in the three-dimensional diagram. So these are the some diagrams which is related to the DC generators, armature winding, and so on. So today we will end our lecture. In the next time, we will see some equations in the DC generators and their calculations.